Industrial automation requires serious capital. Integrating a new robot into your facility is a massive financial bet on efficiency. But according to our partners at Royal Research, the most common point of failure in automation upgrades isn't actually bad hardware. The failure almost always stems from mismatched specifications. This creates a strict capital expenditure dilemma. If you underspecify a machine, you introduce immediate operational bottlenecks that drag down your entire line. If you overspecify, you waste your budget on capabilities you don't need and complicate the integration process. This chart compares the initial flat cost of a robotic arm against the cascading penalties of wrong specs. The hardware fee is small compared to downtime, structural retrofitting, and lost productivity when a machine can't do the job. Selecting an industrial robot is rarely about finding the best machine on the market. Instead, it is an exercise in ruthless constraint matching. To navigate this, we have to look past the marketing and understand which exact specifications directly dictate the output and physical constraints of your floor. Evaluation comes down to 4 core pillars. First is reach, next is payload, then degrees of freedom, and finally controllers. Here is the problem. Relying purely on the simplistic top-line numbers printed on a manufacturer's brochure sets your operation up for failure. A static number printed on a page simply cannot account for the harsh, dynamic realities of a fast-paced production environment. Evaluating these 4 technical specs strictly through the lens of your real-world workspace constraints is the only reliable way to guarantee a solid return on your investment. Let's start with reach. This is the absolute maximum distance a robotic arm can extend to perform a task. Because it dictates the layout of your entire surrounding workspace, reach directly impacts your floor plan. Buying a robot with the exact minimum reach required for your current task saves floor space and initial capital. But there is a sharp trade-off. You leave yourself zero margin for error. If your workspace geometry changes even slightly, your robot becomes obsolete. Payload is equally misunderstood. A common misconception is that a robot's payload refers solely to the weight of the object it's picking up. This flowchart shows true payload variables, starting with the baseline spec sheet payload. Adding the mass of end-of-arm tooling immediately eats into available capacity. Finally, uneven load distribution creates leverage forces that drag the operation straight into a red failure state. When you exceed a robot's true functional capacity, the physical consequences are severe. You will see decreased accuracy, accelerated wear on the motors, and premature mechanical failure. Real-world geometry and tooling gravity dictate your reach and payload requirements. Isolated brochure numbers are functionally useless without that context. Next, we evaluate degrees of freedom, or DOF. This metric links directly to the number of mechanical joints, or axes, a robot possesses. Higher degrees of freedom allow for extreme flexibility. A multi-axis arm can snake through confined spaces and maneuver tools into complex, intricate metal structures. While they allow for these intricate maneuvers, high DOF systems come with a harsh trade-off. They often introduce higher hardware costs and significant programming complexity for your engineering team. For simple, unconstrained pick-and-place applications, a 6-axis system is total overkill. You are paying for agility you won't use while driving up your integration time. Managing those movements requires the robot's brain, the controller. The controller handles internal operations and dictates how the machine interacts with your external factory systems. Modern controllers offer deep software customization and advanced programming capabilities. The trade-off here is human capital. These systems demand a steep learning curve from legacy engineering teams who have to maintain them. You must prioritize controller compatibility with your existing infrastructure. If the software protocols don't match, your expensive new robot becomes an isolated data silo on the factory floor, unable to talk to the rest of your production line. Matching the exact degrees of freedom and controller type to your specific task's complexity prevents you from paying a premium for capabilities you will never utilize. This brings us to the core integrator's problem. How do you test the limits of your reach, payload, DOF, and controller requirements before spending a single dollar of capital? The answer is a digital proving ground. Platforms like RoboDK provide extensive robot libraries and digital simulation tools to map out these risks in a virtual space. This quadrant chart maps simulation time on the horizontal axis against financial risk on the vertical. A highlighted box appears in the high-effort, zero-risk zone. Spending upfront time here minimizes hardware mismatch probabilities, identifying collisions in software rather than physical installation. Inside that digital environment, you can safely identify reach limitations and distribution challenges that spec sheets try to hide. Your process engineers can also evaluate critical performance metrics, like cycle speed and energy consumption, under realistic operational conditions. The upfront time invested in a RoboDK simulation provides the data-driven connection between early planning and final hardware integration, resolving the trade-off between planning time and downstream retrofit costs. To apply these 4 specifications practically, we can use a framework called the deployment matrix. This helps categorize manufacturing tasks and forces you to prioritize your specs accordingly. This graphic separates automation environments into 2 strict columns: tasks that are simple and spacious, and tasks that are complex and constrained. Consider User Profile A, the simple integrator. This type of operation handles basic, highly repetitive applications like end-of-line palletizing. Because their environment is unconstrained, their exact priority is maximizing payload capacity and ensuring simple controller integration. They should actively avoid spending budget on high degrees of freedom. Contrast that with User Profile B, the constrained operator. This team is managing complex manipulation, like internal welding, within tight, restrictive environments. Their priority flips. They must max out their budget on higher degrees of freedom and advanced controllers to handle the programming complexity. For them, maximum raw reach is secondary to pure joint flexibility. Optimizing your automation pipeline is about categorizing your operational environment first, and then buying exactly what that category dictates, nothing more. There is a definitive, non-negotiable rule in industrial procurement: you never guess on specifications. Filter your hardware options through a library like RoboDK. Run the exact simulation against your real-world payload and reach constraints, and let the hard data from that test dictate your purchase order. We focus on this because objective, data-driven decisions will always outperform a manufacturer's marketing promises. A special thanks to Royal Research for their ongoing support in providing the analytical frameworks and data that power these practical insights. Applying strict digital foresight today is the only guaranteed way to secure your manufacturing success and operational efficiency tomorrow.